Today, we will learn about the structural classification and physicochemical properties of quinones. The key point of this section is the acidity strength of anthraquinones, while the difficulty lies in the structures of various quinones. First, let's examine the structure and classification of quinones. Quinones are natural organic compounds that possess a quinoid structure, also known as an unsaturated cyclic diketone structure, or can be readily converted into such a structure, and are thus classified as quinones. Based on their structures, quinones are generally divided into four types: benzoquinones, naphtha-pinquinones, phenanthraquinones, and anthraquinones. Their structural differences primarily lie in the number of benzene rings and the positions of the ketone carbonyl groups. Let's first look at benzoquinones. Benzoquinones consist of one benzene ring and two ketone carbonyl groups, depending on whether the carbonyl groups are located at the para or ortho positions. They are called para-benzoquinones or ortho-benzoquinones. Ortho-benzoquinones is less stable, so para-benzoquinones is more prevalent in nature. Their numbering starts from the carbon atoms where the ketone carbonyl groups are located. For example, the fruits of the Chinese herb Celtis juliana E9, the fruits of Beolea mf, and the flowers of Cinnamon acacia pressil are rich in benzoquinones. Naphtha-pinquinones have one additional benzene ring compared to benzoquinones, with two fused benzene rings. The two ketone carbonyl groups can be located on the same benzene ring at the ortho or para positions, or they can be distributed on both benzene rings. In nature, alpha-1 for naphtha-pinquin is relatively common. The numbering of naphtha-pinquinones starts from the carbon atom at the top of the right-hand benzene ring and proceeds clockwise. Juglone, which has antibacterial, anti-cancer, and central nervous system sedative effects, and vitamin K, which promotes blood coagulation, are typical naphtha-pinquin compounds. Phenanthraquinones are formed by adding another benzene ring to the structure of naphtha-pinquinones, resulting in three fused benzene rings. These three benzene rings are not fused in a straight line, but from a certain angle. Depending on the positions of the two ketone carbonyl groups, they can be classified as orthophenanthraquinone 1, orthophenanthraquinone 2, and para-phenanthraquinone. Representative components of phenanthraquinones, such as tanshin 1,2A, tanshin 1,2B, and tanshin 1,3 in the roots of Salvia mydriaceable bunch, have protective effects on the cardiovascular system, including dilating blood vessels, combating atherosclerosis, and reducing myocardial oxygen consumption. Therefore, medications like Dunshen dripping pills and Danshen tablets are common household remedies for preventing cardiovascular and cerebrovascular diseases in middle-aged and elderly individuals. If you have elderly family members with chronic cardiovascular or cerebrovascular conditions, it is important to ensure that these emergency medications are stored in easily accessible locations and that they are still within their expiration dates. The last category is anthraquinones. Based on the number of anthracene nuclei, they are divided into monoanthraquinones and dianthraquinones. Let's first look at anthraquinones and their glycosides within the monoanthraquinone group. This is the basic parent nucleus structure of anthraquinones, which often has substitutes such as hydroxyl groups at positions 1 to 8. Positions 1, 4, 5, and 8, which are near the carbonyl groups, are called alpha positions. Positions 2, 3, 6, and 7, which are farther from the carbonyl groups, are called beta positions. If anthraquinones combine with sugars to form glycosides, they are called anthraquinone glycosides. The vast majority of anthraquinone glycosides are oxygen glycosides, with some exceptions, such as aloin, which is a carbon glycoside, where the sugar chain is directly attached to the benzyne ring carbon atom of the anthraquinone. Based on the distribution of hydroxyl groups on the anthraquinone parent nucleus, hydroxyanthraquinone S can be further classified into imodin type and alizarin type. If the hydroxyl groups are distributed on both benzyne rings, they are imodin type, most of which are yellow, such as these 5 anthraquinone components in room palmitamel. If the hydroxyl groups are distributed on the same benzene ring, they are alizarin type, which have deeper colors, mostly orange-yellow to orange-red, such as alizarin in Rubia cordifolia L. In addition to anthraquinone S and their glycosides, monoanthraquinone S also include anthro, ol or anthrone derivatives. They are reduction products of the carbonyl groups on anthraquinone S and can interconvert with each other. However, anthranol or anthrone derivatives are less stable and generally only exist in fresh plants. Dianthraquinone S mainly include dianthrones, and dianthraquinone S. A representative component of dianthrones is sen-no-side in senolete, where the 2 anthracene nuclei are connected by the carbon atom at position 10, and each anthracene nucleus has only 1 ketone carbonyl group. The 2 anthraquinone rings in dianthraquinone S are mostly identical and symmetrical, such as in diosgene. Next, let's move on to the second part, the physicochemical properties of quinones. Quinone compounds themselves are colorless, but when chromophores such as phenolic hydroxyl groups are introduced onto the parent nucleus, they exhibit certain colors. Moreover, the more chromophores there are, the deeper the color. In plants, Quinones S and naphtha-pinquinone mostly exist in free form, while anthraquinone S generally combine with sugars to form glycosides. Free quinone compounds generally have sublimation properties. Small molecule Quinones S and naphtha-pinquinone are volatile and can be separated by steam distillation. The solubility of anthraquinone S is greatly related to their existing forms. Free anthraquinone S have relatively low polarity and are thus easily soluble in less polar solvents, such as diethyl chloroform. After forming glycosides, anthraquinone S have increased polarity and are easily soluble in more polar solvents such as methanol, ethanol, and hot water, but are difficult to dissolve in less polar solvents. Plus, some quinones are less stable and should be protected from light during handling or storage. Anthraquinone S exhibits certain acidity due to the presence of phenolic hydroxyl groups and carboxyl groups in their structures. The acidity strength is related to the presence of carboxyl groups as well as the positions and number of phenolic hydroxyl groups. When judging the acidity strength of anthraquinone S, first determine whether there are carboxyl groups. The more carboxyl groups there are, the stronger the acidity. Next, look at the number of hydroxyl groups. The more hydroxyl groups at the same position, the stronger the acidity. When the number of hydroxyl groups is the same, then judge the positions of the hydroxyl groups. The acidity of alpha position hydroxyl groups is reduced compared to beta position hydroxyl groups due to the formation of intramolecular hydrogen bonds with nearby carbonyl groups. Next, please think about it and determine the acidity order of these for compounds A, B, C, and D. Have you all made the correct judgments? Let's summarize together. For free anthraquinone derivatives, the order of their acidity is as follows. Those containing a carboxyl group greater than those containing more than 2 beta-hydroxy groups on the anthraquinone ring. Greater than those containing 1 beta-hydroxy group on the anthraquinone ring. Greater than those containing more than 2 alpha-hydroxy groups on the anthraquinone ring. Greater than those containing 1 alpha-hydroxy group on the anthraquinone ring. Hence, pH gradient extraction can be carried out successively using 5% sodium bicarbonate, 5% sodium carbonate, 1% sodium hydroxide, and 5% sodium hydroxide. Anthraquinone compounds also exhibit weak basicity. They can dissolve in concentrated sulfuric acid to form oxon-ion salts, which then transform into carbocation S, accompanied by a color change. The color reactions of quinone compounds are primarily based on their redox properties and the properties of the phenolic hydroxyl groups in their molecules. They mainly include the following types: by compiling the reaction reagents, positive phenomena, and corresponding structural characteristics of these reactions into a table for comparison, we obtain this table. The above covers what we've learned today about the structural classification and physicochemical properties of quinones. Now, please recall whether you still remember the parent structures of benzoquinones, naphthapinquine, anthraquinone, and anthraquinone. Please draw them on scrap paper and number them. Alright, thank you all for listening. See you in the next class.